Part 2 of Lecture 2, Quantum Theory and the Electronic Structure of Atoms. We will cover wave properties, quantum mechanics, the Heisenberg uncertainty principle, the Schrödinger equation, and look at the single electron system. De Broglie reasoned that the electron is like light and has properties of both a particle and a wave. However, unlike light, the wavelength of the electron can be calculated using its mass. That is, the wavelength is Planck's constant divided by mass times the velocity of the electron. Next, we will do some calculations. So let's calculate the de Broglie wavelength in nanometers of an electron whose mass is 9.1 times 10 to the minus 31st kilograms, that's moving at a speed of 1.125 times 10 to the 7th meters per second. Using the formula for the de Broglie wavelength, we put the Planck's constant in the numerator. Mass has to be in kilograms, and speed has to be in meters per second. The result of the calculation for the de Broglie wavelength is always in meters. Thus, to get the nanometer equivalent, we have to multiply by 10 to the 9th power, which changes this 6.4657 times 10 to the negative 11th to 6.4657 times 10 to the negative 2. Sorry about that. I wrote 9 at first, but it's supposed to be a negative 2. Alternatively, we can calculate the de Broglie velocity in meters per second of an electron having a wavelength of 0.0045 nanometers. This calculation requires us to algebraically manipulate the original equation showing speed equals Planck's constant divided by mass and wavelength. The wavelength has to be converted from nanometers to meters by using 10 to the negative ninth nanometers per meter. After performing the calculation, we find that the speed of the electron has to be 1.6164 times 10 to the 8th meters per second. Such electrons with these types of wavelengths can be used to look at minute particles such as these virus particles here in this tissue sample. In the Bohr model of the atom, we were able to calculate the emission lines that we see in the visible spectrum. However, the Bohr model is inadequate in calculating that for these lines that we see down here in the emission spectrum of helium. The problem comes in is whenever there's an additional electron or additional electrons that then interact with each other. Heisenberg stated that there is a limit to the precision in which certain pairs of physical measurements can be made. He basically stated that it is impossible to know both the momentum, that is, mass times velocity, and the position of a particle simultaneously. Mathematically, it looks like this equation below. Change in x times the change in momentum has to be greater than this value of Planck's constant divided by 4 pi. When taking mass out of the equation, we can either find the change in the position, that is x, or we can find the change in velocity, u, but we cannot know both precisely. With all this information, in 1926, Schrödinger wrote an equation that described both the particle and the wave nature of the electron. This gave a wave function which describes basically the energy of an electron within the wave and the probability of finding an electron within a certain volume of space. Schrödinger's equation can be solved exactly for the hydrogen atom. However, its solution is only approximate when we look at multi-electron systems such as helium, lithium. As a result of his calculations, the Schrödinger wave equation came up with 4 outputs. These outputs, we call them quantum numbers. The first quantum number is the principal quantum number. The principal quantum number we basically saw before in the Bohr model of the atom, where n is an integer value starting at 1 and going up. It basically describes the distance of the electron from the nucleus and will also give us the energy of the electron in the single electron system like the hydrogen atom, as we saw before, where the energy equals negative RH 1 over n squared. However, this equation does not work for elements like helium, lithium, or rather any other element that has more than one electron. The angular momentum quantum number basically describes the shape of the space occupied by an electron. These are the shapes that we associated with s, p, d, f orbitals. A group of electrons that have the same values of n and l comprise what we call a subshell. In the multi-electron system, the combination of the principal quantum number and the angular momentum quantum number describes the energy of the subshell and each subshell has a different energy. For any given value of the principal quantum number, the angular momentum quantum number will have any value starting at 0 going up to 1 less than the value of n. So for example, when n equals 1, the first shell, the value of the angular momentum quantum number can only be 0. In n equals 2, the second shell, the angular momentum quantum number can be a 0 or a 1. It is not both at the same time. And so forth as we go up in the shells in the atomic orbitals. For the different values of L, we get the different orbital shapes. When L equals 0, we get the S orbital, which has a spherical shape. The S does not stand for spherical, however, it stands for sharp. And in any particular atom, at any particular value of the principal quantum number n, there is only one S orbital. For L equals 1, we get the p orbital, or the p subshell, and we will find later that there are 3 different p orbitals available in any subshell. P stands for principal. When L equals 2, we have a d orbital. D orbitals generally have multiple lobes. As you can see here in this picture, there are 2 different types of d orbitals. One has 4 lobes, the other has 2 lobes and a donut. D here stands for diffuse. And then finally, when L equals 3, we have an f orbital. And if you look down at the bottom of the slide, there are 3 different types of f orbitals. However, there are 7 different f orbitals total. And the f orbitals have many lobes with them. It might be a good idea for you to get familiar with the shapes, orbital designations by letter, and also orbital designation by angular momentum quantum number. The third quantum number is the magnetic quantum number, m sub L. It basically describes the orbitals available within a subshell by their orientation in space. Thus, for any given value of L, the m sub L can have any integer value between the negative of L and the positive of L. Thus, if L equals 1, that is, it is a p orbital, m sub L can be minus 1, 0, or plus 1, giving us the 3 p orbitals. When L equals 0, however, m sub L can only equal 0, giving us the designated single s orbital, as I stated earlier. Similarly, for L equals 2, the d orbital, m sub L equals negative 2, negative 1, 0, 1, or 2, giving us a total of 5 d orbitals in any subshell. The final quantum number is the spin quantum number, and it corresponds to the magnetic field that is created as the electron spins. When the electron spins counterclockwise, you get an up magnetic field, and when it spins counterclockwise, you get a down magnetic field. Because of this magnetic fields that these create, electrons can be paired in an orbital, having the same principal quantum number, angular momentum quantum number, and magnetic quantum number. But they have to have different spin quantum numbers so that they can be magnetically coupled in the orbital. This table gives you a feel for all the different orbitals and subshells and shells that occur with the different quantum numbers. When n equals 1, L can only be 0. When L is 0, M sub L can only be 0. And thus there's only one orbital, and with 2 electrons in that orbital. When n equals 2, we have 2 different orbitals, L equals 0 and L equals 1. That's an s orbital and a p-type orbital. And again, when L equals 0, M sub L can only be 0, so there's only one s orbital. However, with the p orbital, M sub L can have the values -1, 0, or 1. This results in 3 different p orbitals in the subshell, and the p orbitals can hold a total of 6 electrons. Looking at the D down here, it first occurs in the 3rd principal quantum number. There are 5 values for the magnetic quantum number from -2 up to +2, giving 5 total orbitals in a D subshell holding a maximum of 10 electrons. The last orbital that we get to look at is the F orbital. The F orbital occurs when L equals 3, and as you can see down here at the bottom, there are 7 different designations from -3 up to +3. As a result, these can hold a total of 14 electrons. Well, let's take a look at these atomic orbitals. First of all, here are the s orbitals. S orbitals are spherical in shape, and there's only one type of s orbital. For p orbitals, because M sub L can have 3 different values, there are 3 different p orbitals. They happen to be oriented along the x, y, and z axes. In the D subshell, there are 5 different d orbitals. As you can see here, 4 of the d orbitals have very similar shapes with 1, 2, 3, 4 lobes. And then there's, of course, this strange one over here, which has 2 lobes and this donut around the outside. F orbitals come even in a greater variety. F orbitals have this one that has 2 lobes and 2 donuts. It also has this type that has 6 lobes. And there are 4 of those, just oriented in different directions. And then finally, the last one has 8 lobes. 1, 2, 3, 4, 5, 6, 7. Pardon me. There we are. There's 5, there's 6, there's 7, and then there's 8 there in the back. There are 2 of these types of orbitals that have 8 lobes. Finally, what we find in the single electron system, the one that we've been principally focusing on is the hydrogen atom. All the orbitals that have the same principal quantum number, that is N, have the same energy. So the 1s is down here, the 2s and the 2p are all in the same line, the 3s, 3p, and 3d are in the same line, and so forth. This is not the case, however, with the multi-electron system, as you'll see in part 3.